Hi, welcome back to my own channel. And right today we'll be talking about chemical equilibrium. So in a moment, we will be discussing what the concept of chemical equilibrium is all about. All right, so just a second as I share my lecture presentation for today. All right, just a moment, 1 minute. Okay. All right, here we go. So welcome once again. In this class, we'll be discussing about Introduction to Chemical Equilibrium. My name is Dr. Abel. What is chemical equilibrium? When a reaction and its opposite reaction runs at the same pace, chemical equilibrium occurs. Now, what does this mean? What it means is that you have a representation where a reaction goes to one direction and goes to the reverse direction at the same time. And what does it represent? You can see the notion here showing is going to the forward direction as well as going to the reverse direction at the same time. When this happens, one can interpret it and say chemical equilibrium has been established. Okay, now what are further illustrations to help us understand this concept? Let's look at this representation, N2O4. Now this is a reactant. For instance, a reactant undergo a certain reaction where equilibrium has been established to form NO2 gas, that is the product side of it. Now, this reaction is said to exist or established an equilibrium system such that the forward reaction is also going back to the reverse reaction at the same time. The description of the system above at equilibrium denotes that both the forward and reverse reactions are being carried out simultaneously. All right, so what is an equilibrium constant? Now, going back to the same expression we had before, nitrogen tetraoxide, now proceeding in an equilibrium pathway to give us nitrogen dioxide. Now, if you look at this equation has both the forward direction and the backward direction. So let's look at the forward direction. What does the equation look like? In the forward direction, the nitrogen tetraoxide, which serves as a reactant, is going towards the product, forming nitrogen dioxide. That is for the forward reaction. Now, what about the backward reaction, which is the reverse process? Now, nitrogen tetraoxide is no longer the reactant. In this case, what then is the reactant? Now, nitrogen dioxide becomes the reactant. Now, this reactant now proceeds to the product, now giving rise to nitrogen tetraoxide. So you can see there is a reverse between the two processes. Now, according to the rate law we've been taught previously, the rate law states that rate is directly proportional to the concentration of the reactant. Note, the rate is directly proportional to the concentration of the reactant. What does that entail? That means the rate of the forward reaction is equal to Kf, denoting the equilibrium constant, the reaction constant, the rate constant, multiplied by the concentration of the reactant of the forward reaction, which is the nitrogen tetraoxide. Now, what about the backward reaction? What does the rate imply? For the backward reaction, the rate B equals to Kb into the concentration of nitrogen dioxide. Now, you can see it is raised to the power of 2, because if you look at the equation in the backward direction, nitrogen dioxide has a coefficient of 2. So the rate law in this case is equal to the concentration raised to the coefficient of that very component, the reactant. So now from here, let's look at how do we further explain this? Now, relating both of the two rate laws together, the rate of the forward reaction equals to the rate of the backward reaction. Now, what is this rate? We already stated that Kf for the forward is the concentration of nitrogen tetraoxide and also equal to the rate of the backward reaction, denoting Kb, which is the rate constant, multiplied by the concentration of nitrogen dioxide raised to the power of 2, which is the coefficient of nitrogen dioxide as a reactant in that equation we just looked at. Okay, now when we rearrange this expression, what is going to be the outlook of the new expression we're going to have? Now, Kf over Kb will be equal to, now interchanging the concentration of both the forward and the backward reaction, we're going to have the nitrogen dioxide raised to the power of 2 over the nitrogen tetraoxide. Now, if you look at the both equation now, we have been able to rearrange this successfully. But now, take note that the ratio of the rate constant is expressed as the equilibrium constant. The ratio of the rate constants is expressed as the equilibrium constant. This implies that the rate constant, the equilibrium constant now is equal to the ratio of the rate constant we just expressed. Now, what is the rate constant? The rate of the forward reaction over the rate of the reverse, which is the backward reaction, which is also equal to the concentration of nitrogen dioxide raised to the power of 2 divided by the concentration of nitrogen tetraoxide. All right, so let's look at further expression that could help our understanding further. Now, consider this reaction, for instance. We have A plus B with a coefficient of small letter a and small letter b. Now I'm going to C plus D with a coefficient, the concentration, molar representation as small c and small d. Now the equilibrium expression for this reaction would be K equilibrium. Now we said earlier is equal to, remember we said the equilibrium constant is equal to or is relating to the rate constant of the reaction. So what is the rate constant if we need to express this? Now we have it that the rate constant is equal to K multiplied by the concentration of the reactant. Now, when we put this expression together, now we're going to have the product side now, take it at the reactant and the product side. Now we have concentration of C raised to the power of small letter c, and the concentration of D raised to the power of the coefficient of D, all this divided by the concentration of A raised to the power of small a, and the concentration of B raised to the power of the coefficient of B. Now, we have been able to successfully now arrange this rate constant into an equilibrium constant. Please don't forget, a reaction that proceeds in the forward direction and also at the same time moving towards the backward direction establishes an expression known as equilibrium. This equilibrium has a constant, but the equilibrium constant is related to the rate constant. So the first thing that comes to your mind, before you can establish an equilibrium constant, you must have an idea of the rate constant. Now, this is an exercise we need to try to put our hands on and see if we actually understand this concept. First, we're going to be looking at the first expression, 2 mole of NO in gaseous form reacting with oxygen to give us 2 mole of NO2 in gaseous form. What is going to be the equilibrium constant for this expression? I expect a feedback from you. And also number 2, we have ethanoic acid, CH3COOH, in aqueous form, reacting with ethanol, C2H5OH, also in aqueous form, to produce ethyl ethanoate, also in aqueous form, plus water in liquid form. Now, I want a representation of the equilibrium constant for this expression. And I'll be expecting your feedback soon. And I know you're going to make a good deal out of this. Thanks for your time. And I'm going to leave you with one word today. I think it has always been a motivation for me. And that word is, you can soar as an eagle in the midst of ducks. You want to become an eagle? You need to select your friends. And your friends must also have ability to scale high altitudes like you. Good luck. See you in our next class. Thanks and bye for now.